All right. Someone near the front row just said C's get degrees, so I don't know what the conversation was about, but do you know what they call the student that graduates from medical school last in his class? Doctor. So, still a doctor. All right. Just an Are You Here quiz today. Who'd like to start us off with a prayer? Anyone? Thank you.
You want to stand up?
Sure.
Dear Heavenly Father, thank you for this day and that we can be here in class to learn and practice more of our math skills. Please bless us and help us to learn and comprehend what is being taught. And bless us also in our efforts to prepare for the test and help our peers to learn as well. Please bless Corey as he teaches. In the name of Jesus Christ, amen.
Amen. Thank you very much. All right, a few things. The exam starts today. The late fee is November 1st, but it doesn't start until 2 in the afternoon. So you can still take it on Friday without a late fee as long as you get in before 2 o'clock. So, and let's see, what's next? Oh, thanks for your feedback. Still, there were only about a quarter of the people that responded. I'm still going through that. Right now, a few themes that I see. Like usually when I get feedback, it's really hard because half the people love the applied problems and half the people don't like the applied problems and stuff like that. But it does look like there's a middle third that are doing really well. The stuff before class is a good resource for them. They learn the material. They come into class, and the stuff they learned before, it really helps them in class if they get, and they continue to learn in class. There's about another third that they struggle with the pre-class material. They still have lots of questions coming in, and so they can't quite follow what we're happening in class, or class doesn't answer their questions because we've moved a little bit beyond that. And then there's maybe about another third. They learn the stuff before class, and they feel like lecture is useless because they feel like we're not going far enough beyond what you were supposed to learn before class, and they feel like it's a waste of their time. So, what would you do as a professor? All right, so here's a few things. So, if you've got questions if you're doing the pre-class material, and questions are coming up and you don't understand, that is great. We know not everyone's going to capture all of the material and understand well from the videos. If it was, we would be out of a job as professors, okay? This material is hard, okay? It's not easy to teach, and so if you've got questions, that's great. We want you to come to class with questions. What we haven't been doing very well, for those that have been struggling, is help getting your questions answered in here. So the times when we turn people loose on problems and you're working, and we've got TAs and I walking around, that's your time to get your questions answered, okay? Paul down and said, hey, Chelsea, or hey, Brinley, this isn't about this problem, but I didn't understand this point that the guy was trying to make on the video, okay? That's your time to get your questions answered, okay? If you're not up to doing the problem that we pose for you, then that's okay. Wherever you're at, get those questions answered. I'm also going to try, when I turn you guys loose, I'm going to try to have a variety of problems, kind of an easy, medium, hard, so you can work on where you're at. So if the stuff I've been doing seems too easy, hopefully I'll have problems on there that are more difficult, that are more challenging, so that you can still be learning in class. Okay? So you can work on the ones where you're at. So right now, those are going to be the strategies I'm going to try. Any questions about that? Okay. Quick explanation about the integral test and the reasoning behind the integral test. If I can find my pen. All right. Here we have a series. Oh, this isn't quite working. Here we have a series. We're adding up 1 over the square root of x. If in a series, it would be 1 over the square root of n that we're adding up. And notice that each of these rectangles here, this rectangle is the same, the area of that rectangle is the same as the first term of the series. If I plug in 1 in for x or in for n, I get 1 over the square root of 1, which is 1. That's the height right here. Okay? But what's the base? The base is 1. So if I multiply the height, which is 1, times 1, I still get 1. It's obviously not to scale. Right? So, but because the difference between our terms is 1, then we can take the heights and multiply them by 1, and now we can think about each of those terms as an area, the area of these rectangles. So for example, on my fourth term, if I plug in 4, 1 over the square root of 4, that's 1 over 2, I get a half. And if I look here at 4, and I go up, I am even with 1/2 right there. Okay? And so 1/4 times 1 is going to be 1/4 still. So this area here is 1/4. So I can think of adding up areas of rectangles, or I can just think about adding up the values of each of those terms. So the areas and the values are the same. And that helps us because we're going to make a connection to integrals, which we can interpret as an area under a curve. So in this case, this is the entire sum. My first value is 1, and my height, that's my height right there. Second height is 1 over the square root of 2, 1 over the square root of 3, 1 over the square root of 4, etc. And if I think of the integral from 1 on, which is going to be larger, the sum of the series or the integral? The sum of the series, because I've got extra stuff on top of that curve. So the sum of the series. But I can do this trick. I don't have to draw my rectangle on the right side. Right now, my height the 1, I've drawn my rectangle on the right side. I could also draw my rectangle on the left side. And if I do that, then it looks like the sum is less than that curve. And the sum is less than the curve, except for one thing. It doesn't show it on this diagram. I'm missing my very first term. My very first term should be represented by a rectangle right over there. Oops. So should be represented by a rectangle right over there. So if I take out the first term, the integral is larger than the sum of the rest. And if I include the first term, the integral is smaller than the sum. And this allows us to make an argument that if, here I'll put on both, you can kind of see it there, that that first pink triangle there and the height of the second purple triangle, they're the same height. Right? You can see that if I took the blue and slid it to the left, I'd get the pink, except I should have one more thing right there. And this trick allows us to make arguments both ways. If the integral converges, then we take out the first term, and that finite value from the integral has to be more than the sum of the series minus the first term. So if the sum of the series minus the first term converges, what's going to happen if I add that first term? It also converges. It's finite. I can't make something infinite by adding one finite value to it. So, and if the integral diverges, then I know from, if I think about drawing the rectangles on the right, if that integral diverges, the sum of the entire series is larger than that, so the series has to diverge. And that's what gives us this integral test. We have a way to argue either way, whether the integral converges or diverges, that the series has to either converge or diverge the same way. Yes? It does. Thanks for bringing that up. Yep. So this is for positive decreasing functions. Okay? Positive, decreasing, continuous functions. Thanks. So positive, decreasing, continuous. If your terms are all negative, then you can multiply by a -1 and make them all positive, and then you can use it. But it does need to be continuous and decreasing. And it actually you actually only need to have it decreasing after some point. It only has to be positive and decreasing after some point, because any first finite value isn't going to make it converge or diverge. All right, let's practice a few examples. Well, any other questions with the integral test? Okay. All right, so here are 4 problems. Okay, 1, 2, 3, and 4, they kind of start easiest to go to more complex. Okay, so if you're happy with if you're good with number 1, you've done problems like this before. I think there was one like this on the website. Don't do number 1, move on. Okay, so start where you think you are. If you've got questions, then about the video or the reading or anything before or any of these, track down one of the TAs, or just raise your hand. Okay, so take a few minutes, work on those. Take several minutes to work on those. Thanks. So I did use Wolfram Alpha to add up the first million terms-ish of this one, number 3, and I almost got to 1 after adding the first million terms. There's a hint on number 3. I'm doing number 2. Okay, let's come back together. All right, so we're not going to spend a lot of time on the first ones. On number one, what's the strategy on number one? You do a U sub. Then you end up integrating 1 over the square root of u, and you end up with the square root of u in there as u goes to infinity, and it goes to infinity. So it diverges. Okay. What about 2? 2 is harder. What's the strategy there? Parts. Integration by parts. So I've done that here. I let u equal my x, and then the derivative was 1 dx. The antiderivative of e to the negative x is a negative e to the negative x. There I actually do a u sub technically. So, or you can do it in your head. And then I did set up the limit. Okay, don't forget to set it up as a limit. Help you think through this. I have to find the antiderivative again of e to the negative x, and that's just another negative e to the negative x. These negatives here become positive, and then this one comes from my antiderivative. And now I have to evaluate. This part is just finite. I really only care if this converges or not. So this part is finite. These, as a gets really large, I'm going to get 1 over a really large number, which is going to go to 0. Here it's more difficult because I have an infinity over an infinity, and I can use L'Hopital's rule, and you end up with it going to 0, 2. So you end up with something that's similar to this second one there. Okay, any questions on that one? Yes?
So it's legal to just do L'Hopital's rule?
Yep. Yeah, because this is the limit of all of these, I can just use limit laws and look at the limit of each one of them as long as they exist. So, yeah. Great question. Great question. So that question, if you didn't hear, the question was it legal to do L'Hopital's rule on just one of the terms? So, yeah, as long as the limits exist, you can separate them and look at the limits individually. Yes? Yes, it does diverge. Yep. Okay. Now, how about 3? So here I gave you one hint on 3. Let me put this up on another page. So we have 1 over n times the natural log of n to the 4th. And so let's rewrite that as 1 over x times 4 the natural log of x, going from x equals 2 to x equals infinity. So we actually should have gone back. We weren't checking actually to see if these are positive, continuous, and decreasing on the interval. So if you actually graph this one, this number 2 that we just did, it actually increases at the beginning. So the graph will look something like this. But eventually it decreases and decreases for the rest on the way out to infinity. So what's it? If you're on the exam and you don't know what the graph of this looks like, how can you figure out if it's decreasing? Take the derivative. That's the easiest way. You can take the derivative and see when the derivative is negative. If after some point it's negative, yeah, I know. We haven't taken a lot of derivatives in this class. I know. So have to do the product rule there. And then reason through, hey, this is decreasing after a certain value. So it is continuous because the exponential function is continuous everywhere where n is continuous. So multiply two continuous functions together, they're continuous. Okay. And they're both positive, so you get positive. So it's positive, decreasing, and continuous. All right. In this case, is it continuous? Could the denominator ever be 0? It could, but not with our bounds. Like if we started at n equals 1, we'd be in trouble because we'd have 1 times the natural log of 1, and the natural log of 1 is 0. We're dividing by 0. So that's why we're starting at n equals 2 here. But after that, this is just going to get, the denominator is going to get larger as n gets larger, and we're still going to be positive. And since the denominator grows, the terms are going to get smaller, so it's going to be decreasing. Okay. So how do we handle this problem here? We can do a u sub, so you can pull out that 1/4. You can set up a limit. To a, and you get 1 over x ln of x. You can do the u sub. U equals ln of x. Du is 1 over x dx. We have a 1 over x dx here. So that gets replaced with just u. So you end up having to find the antiderivative of 1 over u. And what's the antiderivative of 1 over u? Ln of u. And you'll end up having to do, I'm skipping some details here, but you're going to end up having to find the natural log of a as a goes to infinity. Which, what happens there? Goes to infinity, so it diverges. So this one diverges. You end up getting that integral of 1 over u, and we already know the series 1 over n diverges. That's the harmonic series. The integral 1 over u diverges. What's another way for us to know? We actually don't even have to do this integral to know that this diverges. We have something else that we can look at. Just look at that and say, hey, I know that that diverges. It's the p-test for integrals. Since this goes from a constant to infinity, well, it's not 2. I don't know what that is because that's an x ln of 2. So we can use the p-test for integrals. So the power here is 1, and as long as the power is 1 or less, it diverges. And if it's greater than 1, it converges. Yeah, we can do that on this one here. And you guys read about a p-test for series. Now, when you see something like this, does that converge or diverge? Converge. I told you what the sum was before, so you know it converged. But now you can say, hey, that converges by the p-test. You just have to look at that power. Hey, it's 2, and that 2 is larger than 1. Okay, use your first grade math, and it converges. There's a question back there. Yeah. When you've got square roots, when you end up with something like this, no matter how many times you do L'Hopital's rule, you're going to still have a square root in there. And so it's nice to start, you can start dividing by the most dominant term, which is x, because the square root of x squared is going to be about x. So I can divide by x here, I can divide by x there, and then in the denominator, I can start taking that in and do, right, as I take that in, the square root, it becomes x squared. So that's an example. Okay. All right. So what did we get? So what can we say about this series? It diverges. We set up this improper integral. We found that it diverges, and so we know the series diverges. But how can it diverge? I mean, I added up the first million terms. I hadn't even got to 1 yet. How can that diverge? Still increasing to a point where I can't call it 1. Some of these series, they converge or they diverge just really slowly. And you can't just plug it into a calculator and add up a bunch of terms. I couldn't add up, I think I got one series where I could add up 50 million terms, but after that, Wolfram Alpha wouldn't let me add up any more than that. It just times out, or doesn't give you an answer. So it's really hard. So you can't just add it up and see if you get a really big number, and if you get a big number, then you say it diverges or converges. We need another way around this, so have to think about it. But yeah, even though the first million terms, you're not even to 1 yet, you can still go out far enough and get larger than any number. All right, how about number 4? How about this one? Did anyone get this one? Tried? Nicolo? What is it? Nico. You did it by parts? So you thought of it this way? Okay. Nice. Okay. So we tried by parts. What else did people try? Okay. So if you do by parts, you end up with 1 over ln of u. And I haven't done this I'm sorry, if you do u sub, I misspoke, you end up with having to do this thing. And I actually haven't done this by parts, so I don't know where it goes. I'll come look at your work afterwards. But I did want to go this way just to talk about this. How do you do this integral? So you're doing another substitution. Oh, okay. I'm going to call it W. ln of u, and then it's supposed to be Here, hold on a sec. Yeah, so if we solve up here for u, we get u equals the natural log of, u equals e to the w. Okay? Okay, I'm going to pause for just a second. Okay? So, first, nice job. Okay? But I want to pause because we actually don't have to find the antiderivative for this to figure out whether it converges or diverges. So that's what I want to talk about. Okay? So you can start working through to figure out exactly what the integrals are. But at some point, when you do these improper integrals, you actually just have to figure out, is it finite or infinite? So, I don't know what the lower bound there would be to infinity. Is there a way to figure out whether this is just finite or infinite without having to do the strategy like this? I mean, if you can, then yeah, go ahead here. But it's good to step back first and think, hey, is this finite or infinite? And what would we compare it to? The idea was, can we do it with a comparison test? Okay. Here's one I'll throw out there. 1 over, let me do that as x. One over x dx. Okay. Which is larger, 1 over x, or maybe I should just write it 1 over u, I guess. 1 over u or 1 over the natural log of u? Which is larger, u or the natural log of u? U is larger than the natural log, right? And so 1 over those, the larger one, if you have a larger denominator, it's going to be smaller. So you get 1 over the natural log of u is going to be larger than u, at least after some value. Okay, if u is large enough. Like u, once you get to be like 3, you're okay. So, and what do we know about this series? It diverges. Okay, so it diverges by the p-test. So, and we know this has to be larger, so it diverges. Okay, so one of the points of this is at some point when you're doing these, when you're doing the integral test, you only have to figure out whether the integral is finite or infinite. So sometimes it can save you some work from having to go do a whole bunch of things, even though I'm very impressed with you guys. So you can take a step back and be like, hey, actually there's an easier way for me to reason through whether this is finite or infinite. Okay. Nice job. Let me suppose I had this and I added up the first, oh, that's not the first. I'm going to look at the blue. And I added up the first 4 terms. Okay. I know that I'm going to be less than my true series, right? Less than the true sum of my series. I know I have to be less because every term is positive, and so if I haven't added up all of them, I'm still too small. Okay? So how can I get a better estimate? I could add up a whole bunch of terms. We should just do that. Let's just add up a whole bunch of terms. That's not where I was shooting for. Okay, I did a slightly different sum here. This is 1 over n to the 3 halves. And I added up the first million terms, and I got to 2.61038. Okay. Now, does this converge or diverge? It's 1 over n to the 3 halves. 3 halves is larger than 1, so by the p-test, it converges. So this is unlike that other one where we added up a million terms and we didn't even get to 1, the diverge. Here, it converges. Okay. So my question is, I've added up a million terms, but how close am I to my real sum? A million terms is a lot, but am I close? Am I within a tenth? Am I within a 1? How close am I? The computers here don't help us a lot because we can add up a whole bunch of terms, but we still don't know, even if it's convergent, how close we are to the true sum. So we don't know what our error is. But we can use integrals. We can use integrals to get an estimate of how far off we are. So let me write this up here, if it adds a page. So suppose I added up a million terms. Okay? That's got to be less than the true sum. But I would really like to know, I'd really like to have an error. Your estimate isn't any good unless you tell me what kind of error there is with that estimate. Okay? Those of you that are going to statistics, statisticians are awesome at doing that. Actually, in the physical sciences, you're very good. Statisticians or mathematicians, in math class at least, not so much. We're not very good at that. So, yeah, you've got to give me an error. I run I run the 100 meter dash in 5 seconds, give or take 12 seconds. Okay, so right, so the error really depends on how you're going to interpret that value. Okay, so I used to say 10 seconds, but now I'm not sure if I can do it in 10 seconds with 5 plus 10 seconds. Okay. But if we think about this the right way, then we can actually use integration to estimate how much stuff we have from here on out. Notice that as we go out further and further, the difference between the curve and the flat line on of the rectangle at the top is really small. That error is going to be really, really small. So we can add up a whole bunch at the beginning, and then we can approximate the sum with the rectangle from there on out. Okay? And I won't go through the reasoning right now, but if we start at one more than where we ended and find the integral of our series and add it to our original sum, we're going to get a lower bound. But if we start at the same sum, the same term, same x coordinate here, these are the same, then we're going to get more than the true value. It has to do with like if I added up the first 7 terms, well, actually if I added up the first 8 terms, so right now, if I think of the blue part, the first 8 terms looks like that. But then if I start at 8, if I actually start my integral at 8, then I kind of double count this area. So I end up with more than what I actually have. Because I count this area with the rectangle there, but I also count almost the whole area because I count it underneath the curve because I'm starting my integral right there. So I end up with a higher estimate. But if I start right here and think about the pink ones, they're going to be smaller than they're going to be underneath the curve, and you can argue that it's going to be an underestimate. So, not a great explanation for this quick, but that's why. Like you can think about those rectangles, either one side or the other side, and you can give arguments that hey, this one has to be larger, this one has to be smaller. All right. So my question for you is: was this sum here 2.61038? If I added up, well, if I knew the true sum, would it be, and rounded it, would all those digits be the same? Would any of those digits change? Let's see. Here I have the integral from 1 to infinity, from 1 million to infinity, and added it to our first estimate. And actually it's different. This is 2.61238, and the original one is just 2.61038. So I wasn't even within 1,000th of the true value there, even though I went out 1 million terms. So, all right, have a great day. You're welcome.
Thanks for the recording.
You're welcome. See ya. You're welcome.